Uh, Hopefully everyone has enough coffee, caffeinated. Yes? Yes? Yes, okay. Anyway, I don't work for Starbucks. I am not selling coffee. But I'm going to talk to you about resource management, a framework we are developing at Docomo USA Labs. And for those who don't know, Docomo is a Japanese telecom company. It's the largest mobile carrier. And everyone is asking me where we are located. We are here in Palo Alto. So I have some colleagues with me here as well. So what I'm going to talk about is a resource management framework that we are developing on top of XCP. So to give you some motivation on why we are doing this, let me start with a simple scenario, somewhat simplified, where you have a shared infrastructure, like you have a data center like Google, Yahoo, and other companies have, and you have multiple applications accessing this shared data center. Some people call it cloud. We can call it whatever we want, I guess. But now, what are the requirements of these different applications, right? So I have here two applications, web search and data analytics. And we know that when we do web search, we want to get the response back as quickly as possible. On the other hand, when we are doing data analytics, maybe we are just looking at how to analyze large amount of data. So if you kind of turn that into systems requirements, web search requires low latency or low response time, and data analytics requires high throughput. So we have different requirements for different applications. And these applications might be willing to pay a good amount of money to get to these goals. When I say money, not really real money, but this might be the utility of that application for that company. For example, for Google or Yahoo, maybe search is more important than doing analytics. Now, how are these applications hosted right now? Sure, Google maybe has much better mechanism, but traditionally, we have applications being hosted by physically partitioning the resources. So here I have three applications. Application 1 has two tiers, web and database tier, you can see at the top. And application 2 and 3 are single tier, and they are all hosted in different physical machines. So as you can imagine, this might be wasting resources when these applications don't use the full physical machine. And they are difficult to manage as well. Now we all know that we can virtualize, and virtualized data centers are big, everyone is doing it, and we can move these applications into much fewer machines, all that. So we have improved utilization, and all these benefits you have seen like many times, hundreds of times. Now, we have created a new paradigm. We have this virtualized data center that everyone can use. People can share, people can write applications that share the data center. Now the challenge is how to allocate resources to these different applications, like web search or data analytics, to meet their goals. So that's the challenge. And that's one of the challenges we are trying to address here. So let me go a little bit deeper into all these challenges, right? Why is this question tough to answer? So let me start with challenge 1, where a developer is trying to scale their application. Don't try to pick problems in this code. It's not real code. It's just a simplified example of how a developer might write a scalable application. Sure, I'm sure you can't write it in one slide. But let's say they start with provisioning the VMs and start running the experiments. And then they try to monitor the application and figure out if there is any problem, do something. And then also, since these are VMs and we are in a shared data center, we want to consolidate. But there are three critical questions that come up when you have such kind of scalable application. First question is where to provision these resources, or where to provision these VMs onto what resources. Now the next step is once we have these VMs provisioned, they're running. Now if there is a problem, first thing is to figure out why that problem is happening, and then figuring out what to do with it, like scale up, scale out, or what migrate maybe. And also, of course, how to consolidate VMs, where to consolidate, and deciding when to consolidate. Now also, like the cloud providers want to do the consolidation at a service level, like they want to combine multiple services. rather than VMs in a single service. So again, all this is good, but this is very complicated. A developer doesn't want to deal with this. So where we want to get to this holy grail where the developer can say, I want to deploy the service and then auto scale. That's it. Hopefully everything is automatically figured out. And the second challenge is that resource management spans through multiple layers. I think most of you have seen this kind of layered architecture. So we have the hardware at the bottom, and then it's something called IaaS, or infrastructure as a service, gives you an abstraction of this hardware so that you can build a virtualized infrastructure. Now on top of that, you can build a platform like Google App Engine, which is called Platform as a Service. You can build on top of that, and then services are running on top of that. Now the crucial thing is that resource management runs through all these layers. And the question is how to figure out or how to pass information between these different layers so that we are doing the right thing for the service or for the cloud provider. Now the challenge number 3 is that, let's say we have decided to do this scaling. So what primitive to use for the scaling is the question. So let me start with introducing a few primitives. So what I call as slicing is you can allocate, you can slice the resources in a single physical machine or on a network to a single machine, on a single physical machine, sorry. So that's what I call as slicing. So here, especially in Zen, this is very fast. You can slice the CPU to different VMs efficiently, but it is limited to one physical machine. Then we have live migration that can handle overload. You can move VMs from one physical machine to another, and then maybe balance and all those things. So we know that it has very small downtime, but it has its own overhead. And there is cloning that is proposed in last year in Eurosys called Snowflock that allows you to statefully clone a VM and create a copy of it. So you could build a reactive scaling mechanism on top of that. So that is one way to do it as well. And another technique that we are working on called as live replication. I won't go into any of the details of that, but think of it as splitting a VM into multiple VMs and still maintaining the network connections that were sent to the first VM. So this is also a very good strategy to do scaling, and we are planning to we submitted to Hot Cloud and planning to present there. And but there is some overhead. But now we have all these technologies, we have all these primitives that have their own pros and cons. How to figure out which one to use? So how to combine all these primitives to achieve the goals? So that brings me to the perfect resource manager. I don't think there is, you can build this, but at least we can try. So I won't read the whole definition that I wrote there. But what we are trying to do is automatically allocating resources to achieve high utilization and high application performance. When I say high utilization of the resources. So that's what we want to do. Now, we're trying to build this perfect RM, which obviously we can't, but we are trying. And I want to call this the ultimate RM. Hopefully we'll get there maybe, I don't know, 2-3 years. But XRM that I'm going to talk about today is the 0.0.1 version of this that is built on top of XCP. And I'm going to tell you more details about that. So that brings me to the outline for the rest of the talk. So to recap, we have lots of challenges in resource management. And I think I outlined all of them. So we have 3 different challenges. And we are going to build this XRM, and I'll explain how we design this and implement this, and our experiences with using XCP as our platform. I'll conclude with that. Okay, so we have this automation part, right? That is the first bullet I had. I want to automate the resource allocation. Now, how do we do this? Well, this is a quote from a nice book, Feedback Control of Computing Systems by Hallerstein and others. So this quote actually says that almost any system that is considered automatic has some kind of feedback control. That's a pretty nice quote, and it is actually true. So we try to build XRM as a feedback control system. And I won't go into too much details of what is feedback control, what is control theory, how do we apply all that. I'm going to give you a high-level overview of how that works. So before I go into that, let me go back to this multiple layers I have shown you earlier slide. Again, we have hardware, and then we have the infrastructure as service layer, and then platform, and then the services. Now, the RM's job starts when the service developers or service owners want to deploy something, and they send a request to, let's say, platform layer. We can argue whether this is a good layered strategy, but this is one way to do it. Now, platform layer can do application modeling and can decide what kind of resources are required to achieve that service goal. Again, I'm like glossing over the details, but let's say it knows how to send the resource request. I'm calling it a slice because think of it as slice as a set of virtual machines and some virtual network. For this presentation, let's not worry about network at all. Let's just say bunch of VMs that need to be scheduled or provisioned, and the request comes in. So now the IaaS part of resource management, it only knows about the virtual machines or the hardware resources, but it doesn't know anything about what is running inside the VM, as in what is running in the application. Now all the magic happens in this automated control loop that I'll tell you in a second. And this control loop has a controller that can make automatic decisions and then make changes to the slice. When I say make changes, like let's say increase the amount of CPU for a VM, move it to another place, and things like that. And these slice changes are propagated back to the platform layer. Now XRM, I think you have already realized this, but XRM is the IaaS part of the RM that is built on XCP. So let me go into a little more detail into the feedback control loop. Again, this is not, if you're a control theory guy, this is not accurately depicting the control loop, but this is for illustration. So we have three main actions or three main tasks. We do the monitoring first, and then control, and then once the control algorithm decides what to do, you do the action. Now, how does the controller decide what to do? That can come from a model. And in control theory, this model is usually developed using like physical laws, but for computer systems, we don't have that, so maybe we can use black box models. I won't go into those details, but if you have a model of how to allocate resources to achieve certain goals, then you can do it. So right now, this is the current implementation as it is now. So we have the XCP monitoring, XCP statistics module that actually gathers statistics from XCP and then passes it on to a monitor module that does some analysis and then passes it to the controller. Now, why do we need this analysis? Because there might be too many metrics, and maybe that algorithm doesn't want to deal with all the metrics. So I'm talking about algorithm, but I haven't described what it is. So that's the beauty of it. You can build your own algorithm and plug this in, and it can be as simple as a round-robin algorithm, or it could be complicated stuff like one of the auto control system I can show you. So given this algorithm, the algorithm registers for certain events. So what are these events? These could be like VM mutilation, overload, VM high CPU overload, or any of the other events that might cause the algorithm to take a certain action. Now, once the algorithm decides what to do, it passes it on to the lower layers, and we have here OpenFlow also for the networking part. We can ignore that. But XCP takes the request for the CPU part of it and then does the right action. So as I mentioned just now, it's an event-based framework. So you can build your own algorithm that can register for many of the events that this statistics module provides, and then you can do something with these events. And that something is your control logic. And you can build any kind of algorithm that matches your goals. And the key idea here is that we have abstracted this algorithm part. And when you write the algorithm, it will be like a Python file with one function in it that says run this algorithm. And that function is what your control logic. And you have to write only that part. So what algorithms can you implement? Anything you can think of. But to give you a flavor of what can be done, I'm actually showing one system that I developed as part of my PhD work. And this was published in Neurosys last year. So it's called autocontrol. I won't go into details again. But it uses feedback control to figure out how to allocate resources to multiple VMs in a distributed fashion based on certain goals. So how that is done is, again, you can read the paper. But these are some other things that you can do with this framework. So we have somewhat constrained you to a feedback control way of doing things, but maybe that's a good thing because you can solve many problems. So that is some feedback I would like to learn, whether feedback control system is the way to go. So that finishes the design part of it, and I would go into details of how we implemented this and preliminary results. So, to implement, like at least right now, we tried to implement these features. These are not finished, but what we tried to do is all these what we call as auto-star features. It is like auto-scale, auto-migrate, or auto-replicate, and auto-clone, things like that. And auto-scale as the primitive that can do everything. But we'll get there. We haven't done everything, but now we want some external control to the controller itself, because the controller in control theory way, it should be completely automatic, but in real systems that's very difficult to do. So we need to expose something so that you can control the controller itself. And of course, as I mentioned to you, pluggable algorithms and then extensibility. So it's implemented in XCP 0.1.1. That's probably released in February, I think. But our part of XRM is written in Python, and it uses the Zappy tool stack to connect to XCP. And we have pluggable algorithm also written in Python. And right now we have like 4 very simple algorithms. This is nothing earth-shattering or new, but these are implemented and these can be tested as well right now. So bin packing, I think most people are familiar with. So it tries to pack the VMs onto one machine as much as possible. And then bin packing combined with live migration can give you like a workload balancing kind of algorithm. And you can, of course, tune it. Then there is a random host selection, which is like a easy way of like deciding where to go. And then round robin, I think, again, most of you are familiar. It just chooses one physical machine after another. Now, one of the neat things about what we have done is that we have also built a simulator that can let you play with all these algorithms. So you wrote this complicated algorithm, and you don't have like 1,000 machines to test it. So that is where this simulator comes in. Now, you can play with the simulator completely, but you also want to run the algorithm on real machines and then go back to your simulator. So that is what I think is the best feature here, because you run your algorithm on real machines, then the simulator collects all the statistics, all the VM utilizations, all the decisions that have been made, and then records them. Then you can replay them in your lab, in your simulator, and then with a new algorithm. It will have the same VM utilizations, same machine state, but your algorithm is different. So that way you can try many different things. So I'll show you an example of that here, just after this slide. So we tried to evaluate XRM. This is very preliminary, and I wouldn't read too much into this anyway. So what we have tried to do is create random utilizations in the VM, and there are random slice, meaning set of VM requests, and then we tried to compare these 3 algorithms. I'll also show some of the results with my autocontrol as well. So this is comparing 3 algorithms. Remember that there are 5 hosts, and on the y-axis you can see the sum of the utilization of all the 5 hosts in like 5 different bars, right? And on the x-axis you have time, so the experiment runs for a certain amount of time, And at each interval, certain slice request comes in. That is not shown here, but you can assume it's like a random slice request. And once that slice is scheduled, then you have random VM utilizations. Now you can see at the bottom, we have the bin packing, which tries to pack all the VMs together. And you can see that like at this interval 2, there is only one machine that is occupied with VMs. All other machines don't have any VMs. And on the other hand, if you choose random host or round robin, you're actually using a lot more machines. So if you take round robin, you're using all 5 hosts and thus wasting energy. Similarly, random host can choose some set of machines. But bin packing, it always tries to pack things together. And as simple as bin packing is, it works. It is pretty efficient as well. So already we are at a point where we can actually deploy this and do like some kind of energy reduction as well. Now, these experiments are like the auto control system. I haven't given you the details, so I just give you a high-level overview of what I did for my work last year. So the reason I'm showing you this is that what all things you can do with a feedback control system. So here I have an experiment that is running on like 20 server nodes, 4 VMs each, total 80 VMs, and then 20 client nodes, which are generating certain requests. So let's right now ignore what exactly they're doing, but I'll show you a graph in a minute. So we have a mix of applications. The key thing is that after a certain time, we increase the load on half of these VMs chosen randomly. So it might look like this. Like sometimes all the 4 VMs on a physical machine, they don't have any overload, or all of them are underloaded because that physical machine was not chosen during the random choice. But sometimes there might be 1, 2, 3, or 4 VMs that have overload. So when I say overload, that means they have the higher number of requests coming in, and they cannot meet their goal. So first 2 cases, you don't really need control because it can normal Zen scheduler can slice the VMs so that they can handle the requests. But in this case, Zen scheduler cannot help, and auto control can help, because auto control has a model of how to reorder the CPU utilizations. Of course, So the fourth case is where you don't have enough resources. All the VMs are overloaded, and you don't have enough resources. You can't do anything. So all that is there. So let me show you an example. Let me show you the result of all these 80 VMs. So on the y-axis, you have all these applications. And then initially, everything is green, meaning that you are meeting performance goals. Don't worry about the different shades of green right now. But after a certain time, I increase the load in half of the VMs, as I described earlier. So you can see some red dots, which means that you are not meeting the goals. Now, in case of auto control, what it tries to do is it will reorder the requests. It will reorder the CPU allocated to the VMs so that you can meet goals for some of them. You can still see some red dots because sometimes you don't have enough resources. So in that case, maybe you should use migration. So that's a topic for another day. So I'm showing this to show an example of how good a feedback control can work and what all things you can achieve. So I'm hoping people will develop more of these for different, like for example, one could develop a feedback control system that reduces energy. And it can take the measurements from the VM, the energy usage of a VM and the physical machine, and try to do something intelligent. There are many proposals like that in research, in academia. So that is something you can build on top of this. So to summarize, resource management in cloud infrastructures is complex. We know that there are multiple layers, and we have to do multiple layers of resource management. And there are complex primitives, like I mentioned, slicing, migration, all these things. And you need to use them to make complex decisions to meet your goals. Now, what we are trying to do is we are developing feedback control theory-based resource management. And you don't have to worry about feedback control. You just have to worry about your algorithm, because the feedback control system is already provided to you. You just need to plug in your algorithm. So that's what the next bullet says. So XRM basically gives you that framework where you can just plug in your algorithm. Of course, complex algorithms like order control can be developed. This is not integrated yet, but things like that can be integrated. And we are planning to do more algorithms. Now, before I finish, I just want to summarize also our experience with XCP. And before that, so what we are trying to do is build a research cloud based on XCP and do some development of some algorithms for managing virtualized infrastructures, including both virtual CPUs and virtual networks as well. So other than XRM, we're also putting our efforts into adding fault tolerance. And Ken, one of my colleagues, is here. He has worked on that. And unfortunately, we can't talk too much about that. And we're also trying to build a web-based GUI for XCP. And I think XCP project update, during that, you mentioned that there is going to be a web-based GUI. So maybe this can be integrated with that, or maybe not. So let me quickly show a screenshot of this. The slide name is in Japanese, so don't worry, I can't read it either. I think it says something like GUI screenshots. Let's just say that. So we do have that GUI, and we are using that to deploy our VMs and do some experiments. So just to talk about a few pain points we had, using XCP distribution itself is a bit difficult, because we want to use something like CentOS or Red Hat Enterprise Linux. And also, XCP docs, they're not yet mature, and that needs to be improved so that it is clear what is available, what is not available. Some of it is mixed with Citrix Zen servers features. And GUI I already mentioned. Oops, sorry. That was the last slide. Sorry about that. Yep, so this is the final slide. So what we want is a feedback from all you guys. This feedback control stuff doesn't make sense or something like that. And I can explain. So, so talk to me after this presentation or through email, and we can. So what we are trying to do is get feedback and trying to figure out whether we can incorporate this into the community, and whether anyone is interested in supporting it, or whether anyone is interested in being involved, and any questions you have. Thank you.
Thank you. Do we have any questions?
So one of the key issues with the feedback control system is that there's a built-in delay. You collect a lot of information, you process it, and then by the time you know what you want to do, the world has changed underneath you. How do you handle that?
Right, yeah, that's a good question. So in control theory, that's called the control interval. So within the control interval, it can be as small as 5 seconds. So it very much depends on how good your actuator is. When I say actuator, something like setting the CPU share or OpenFlow slice. So if it can do it within a millisecond or even faster, then you can actually adapt to it. Of course, the monitoring part also has to catch up. So these two, if they are fast enough, you can do it. The control itself is very quick. So I would say that if the change happens within the control interval, no one can do anything. Even non-control theory-based system also cannot do much. But if it is over 2-3 control intervals, it can handle.